Okay, we start this video um, introducing systems of equations. Uh, when we have a single equation with only one variable, say 2x, so let's label this as example 0. 2x plus 3 equals 15. Okay, so we're looking for an input x in this case so that it meets this requirement that whatever that number is times 2, adding 3 to it, we end up with 15. That is what I would call a requirement on x. This number has to meet this condition or a condition. It is a special number that will do that. Um, so that is one example of one equation. We don't label this as a system of equations. This is just one equation. If we have two requirements, say, uh, 2x, so this is a different kind of problem, plus 3y equals 15. In addition to that, we want perhaps x plus y to be, and I'm just making this up, so let's say 6, all right? So now we're looking not for one number, but a combination of numbers that meet this requirement, those two requirements together. Oftentimes we put a left side bracket without a right side bracket. That's just the way people have done it, so I'm not going to change that. And that indicates that the two requirements have to be met for those two numbers. So we're not looking for just one number here. Here we're looking for two numbers, x and y, that meet those two requirements at the same time. Now, let's just look at the second equation. There are many pairs of numbers, x, y, that meet this requirement. So for instance, 1, 5 is one such solution. 1, 5 meets this requirement that added together, they give us 6. There is, for instance, -2, 8, because when we add those two numbers together, we get 6. And then there is some ones that are fractional. So let's say 1.5, which is 3 halves. And then we would have to have 4.5, which is 9 halves. So those are solutions. And the solutions are not just one number. Here, the solution is just a number. 6 is the solution. Here, possible solutions only for the second equation are those. The solutions for that equation are more complicated. Let me think. So for instance, 3, 3 is a solution, isn't it? Boy, that comes up too quickly. But then there's more solutions. For instance, 0. Okay, so first of all, there are many more. I'm going to put ellipses here, indicating there are many more solutions to this equation. What about solutions to that equation? Well, one of them is, for instance, 0, 5. If x is 0 and y is 5, that adds up to 15. So that is one solution. Another solution is 7.5 times 2 and 0. So 15 over 2, 0 is a solution. Let me think. How about -1? Or let's just do negative. Yeah, -1. And let's see, if x is -1, that is -2. If we move that to the other side of the equation, we end up with 17 divided by 3, 17 thirds. Yeah. So there are many solutions here. Now, the list of solutions here and the list of solutions here may or may not intersect, may or may not have something in common. If they have something in common, that is the solution to the two equations. So one solution that I didn't have here in this list of solutions is going to be 3, 3. I put 1, 5 because that adds up to 6. I put negative 2, 8 because that adds up to 6. Well, 3, 3 also adds to 6. So that is part of this set. So pretend this is a set. All right. And then 0, 5 is a solution to that equation. By the way, 0, 5 is not a solution to this equation because 0 plus 5 is not 6. 15 halves, 0 is not a solution to this equation, even though that is a solution to that equation because 15 halves plus 0 is not 6. So there are many solutions here, almost all of them, almost, that are not solutions of that. Now 3, 3, let's see. 3, 3 will do because 2 times 3 is 6, 3 times 3 is 9, and 6 plus 9 is 15. So this is a solution to that equation. In other words, we have there. This solution is a solution for this system, and that solution is a solution for that system, not that system, that equation rather. So again, this is a solution to that equation among all the solutions. This one is one of them. And this 1, 3, 3 is a solution to that equation among all the solutions to that equation. So, and the two sets don't intersect except for that one. That's the only place where they intersect. There is no other place where they may intersect. So that is the solution to that system of equations because it is a solution to that equation, while it is also a solution 3, 3 to that equation, to both of them. Yeah. And that's what we are looking for. Now, this method of going with a list and going with a list, I mean, if we are very lucky, it would work. But it's like throwing a dart in the dark. Will you hit the target? Maybe, you know, or maybe not. We don't know. It could happen that we get the answer by trial and error. But there is an infinite number of elements to test, and sometimes, actually, oftentimes the answer is not this nice, 3, 3. You know, oftentimes they have fractions and other things like that. And so, which fractions are we going to try? Are we going to try halves or thirds or fifths or sevenths? We don't know. So, by trial and error, this could work, but it's not a very precise way of going about it. So we're going to investigate different methods to do this. So this is just to give us an idea of what is going on. And now we're going to look at some methods to solve this system of equations. So one method is the graphical method. So I'm going to do 2 again. Let's stay with the same 3y equals 15, and then x plus y equals 6. So even though this is a new example, I'm using the same system. We know what the answer will be, but let's analyze different methods. And it is sometimes a good idea to learn new methods with old problems, because I believe it is better to learn by changing one little thing at the time. At least that's the way I feel comfortable when I'm learning something. Instead of changing something all of a sudden, very quickly, if I change one thing at a time, then at least I have an idea of what's going on. It's easier to extend learning by changing one thing at a time. The scientific method also works that way. When we do experiments, we change one variable. So there is something to be said about that. Anyway, so we're going to try the graphical method. Graphical method. It's a very important method to learn, especially since we have advanced calculators that can graph this very well. So the graphical method says, graph this equation, you know, y equals, so I'm going to move the x over. So we have negative x plus 6. That means the slope is -1, and the y-intercept is 0, 6. And we're going to solve this equation for y. They don't have to necessarily be in the same order. Perhaps I should have put them in the same order, this one first and this one second. This one is so easy, I cannot help to just grab that one and start working on it. and then this one second, because that is requires more work. So we move the 2 over to the other side, so we have negative 2x, but then we divide by 3, so we have negative 2 over 3x, and then the 15 stays there, but then we're going to divide by 3 if we're solving for y. So we're going to end up with 5. Okay. Now, there's a drawback on the graphical method. We have to solve for y. Sometimes that can be a little long, usually not too long, because the linear equations are only so difficult. But then the other thing we have to do is we have to graph this very, very carefully. So for instance, in this case, we got to go up. To graph this, I'm going to go up 6 units. So 1, 2, 3, 4, 5, 6. And then the slope is -1. So the graph is going to go down 1, 2, 3, 4, 5, 6. Yep. So because the slope is -1, every time we go over, we're going to go down by 1, over 1, 1, and so forth. So if we start out with 6, every time we go over and we go down by 1, it is going to take 6 units across to get all the way down to 0. I'm going to use a ruler to make my line reasonably straight, although somebody could argue, well, your axes are not very straight, so I don't know if that's going to help. The other line goes through 5, 0, 5, and it has a slope of -2/3. So every time we go 2 units over, and by the way, some people say, well, I don't know, they don't want to do this because they have to graph. Yes, it is a good thing to graph, because that is a skill we want to continue practicing. Graphing lines is a very, very good skill you want to have handy. So start with 0, 5, that is the y-intercept, and the slope is -2/3. That means that every time we go 3 units over, okay, let me think about that. Rise over run, yeah. So every time we run 3 units, so by the time we get to 3, this is going to drop down by 2. So 3, and then we're at 5. So 1, 2. Well, the graph is going to hit the intersection point, and then 3 over is going to bring it down by 2 again. So now we're going to be at 6, 1. So again, we use the ruler, and we have this kind of line, and we can observe that they cross at the point when x equals 3 and when y equals 3. Okay. So the graphical method is as good as our graphs, as our ability to graph the functions that we have, the lines. Those are going to be lines. If we're not very good at solving the equation for y, or if we are not very good at graphing, or if our graph is very it has too many flaws, because we have to graph things reasonably well. The slopes have to be correct, the units have to be, so I cannot sketch this too much, in the sense that I cannot change the scale really too much. We want to be more precise. And sometimes we don't see this point very well. What if if the answer was 2.9 comma 3.1? You know, so what if the point was very close to 3.3 and we think the answer should be 3.3? So that is a problem. Now you could say, well, you can always put it back into the original system of equations, which we should, to make sure that we have the correct answer. So we should put the numbers we think the answer are in here to make sure. But what if the numbers are not? Because this is very visual and our eyes can see only so well. What if the answer is supposed to be 3 point? So let me write this down. Okay, so this method is as good as the precision of the drawing. Now you can do that with a graphing calculator. The graphing calculator, you set this to be y1, this to be y2, and sometimes the point is not on the standard window of the calculator, so you have to figure out where the point may be, and that can take a while. So you might have to change windows. You gotta maybe zoom out and then zoom in back into the point where you think the intersection is. So there's more work to that. Okay. But be aware that this method is, again, as good as the graph, as precise as the graph. If this is, I mean, we can guess the answer is 3, 3, but nothing guarantees that the answer will be an integer. What if the answer was supposed to be, okay, so I had the solution being, something like 2.978, comma, 3.027. Okay, so if the solution was very close to 3, 3, but it wasn't exactly 3, 3, it was something really close to it, then it would be really, really difficult for us to see the solution. Okay, had the solution been this, then this method would not be as good. Not be as good. Why not? Well, look at the pixels. When you're drawing this, or even the ink of the pen. Those 2 points, this point and that point, could be so close to each other that practically the pixels are one on top of the other. We cannot differentiate. And zooming into this, zooming in, you can only zoom in so much. Even with a calculator, the calculator will help, no question about it. Will make things more precise. But even the calculator cannot get exactly to an answer necessarily, because the calculator eventually runs out of digits. And some solutions will have an infinite number of digits. So is this method good? It is very good in the sense that it gives us a very good idea of what's going on. The outputs, the points here that start diverging away. So we have a good general idea of what's going on. That's why this method is very good. Also, this method can be used for other systems of equations which may not be linear. Yes. And it does, especially if we use a graphing calculator, this method is very good in the sense that it can give us an approximation that is almost the exact answer. Not the exact answer, but very close to the exact answer. So the graphical method has a lot of value to it. Don't neglect it. Tons and tons of books have in their textbooks, have in their exercises, many problems that you should do using the graphical method. If nothing else, it helps you understand or solidifies your understanding about how to draw straight lines. And drawing straight lines is something very basic. Every student of algebra should know how to do. So please practice this graphical method. Is it the best method? Not necessarily. It isn't, because the solution is as good as the precision of the graph. But having said that, it is still a very, very good method. It's not a perfect method, but it is a good method. Okay, after that, after this example, now we're going to do examples where we use algebraic methods. Before doing algebraic methods, though, let me tell you about the cases. Okay, so we're going to do algebraic methods next, but let me show you the cases. There are 3 cases when we have two systems, rather one system of equations with 2 equations and 2 variables. So 2 equations and two variables. So this is, we're specializing in this. We have three cases. Leads to three cases. Okay. So the two equations, and it is good to see, to have seen the graphical method, because now we can show the three cases graphically. It could happen that the two lines are parallel. And as you remember, in geometry, in Euclidean geometry, um, if the lines are parallel, that means that they don't have an intersection point. So they will never converge into one point. They will continue forever and ever have the same distance between them, whether you go in that direction or in this direction. So that's one case. I'm going to label it as case one. And in this case, there's no solution. No solution whatsoever. Okay, and it happens that the two conditions are such that they contradict each other. We're going to do examples of that when we get into the algebraic methods. Case two is when they do intersect very nicely into a point. So they're not, they just cross each other. And because the lines are straight, they're not going to bend to cross back into a second point. If they cross in this fashion and they're not parallel, then they are going to cross exactly at one point, not 2 points, not 3 points, just 1 point, and that's it. So in this case, we call the system consistent with a unique solution. So there is exactly one solution. Now, the next case, and by the way, the numbers I'm using, case one, case two, and case three, is arbitrary. Another teacher could call this case one and then case two and case three, or another teacher could call this case one, case two. It doesn't matter. I'm just, so this is not written on stone that it cannot change. It depends. The cases are the same, but the way teachers may number them could be very, very different. But the case three is a really weird one. In fact, I'm going to put it here. WEI, weird one, weird case. Yeah. I mean, people understand this. People understand this. The weird part about this case is that one line is on top of the other line. Well, if they're on top of the other line, that means they are the same line. So we're going to look at the intersection of a line with itself. Yeah, so this is so where do they intersect? And by that, what we mean is what points do they share? So intersection has to do with sharing a point. And that's seen here, those are the points of one of the equations. Those are the points of the other equation. This is a point that they share, and that's the case here. I mean, the slopes are going to be different, but the idea is that they intersect at one point. Here, they don't share any point at all. How about that one? Case three, that's the weird one. Mind, it is weird because if we have a line on top of the other line, aren't they the same line? Yes, they are the same line, but yet we are comparing a line with itself to see how much they intersect. And of course, they intersect everything. So it is, I have to admit, this is a weird case. However, we, in mathematics, admit those cases. We take them into account because otherwise we have to write too many exceptions. The writing of the theorems that we write, the results that we write in mathematics, would take maybe not twice as long, but it will take a significant amount longer if we don't take that in this, if we don't admit this case as a valid case. So it's a weird one. However, it is, we consider it as valid. Okay, and it has infinitely many solutions. Infinitely many solutions. Okay. Please be aware this is weird. If it looks weird, just embrace the weirdness of it and move on. Don't try to fight it. Uh, we don't want to be philosophical about it either. Well, it's the same, it's not the same. No, 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 no. Let's be practical and say, okay, because all the teachers, to the best of my knowledge in the whole world, admit this. All the math people admit this as a valid problem. So we're not going to fight it. We're just going to embrace it, admit it. And there's a good reason why we do admit it. Again, to be repetitive, the reason we admit things as opposed to um, exclude them is because otherwise the writing of the properties, the writing of the theorems, the results will take longer because we have to do, okay, case one, case two, case three. We want to put them all together into one case, and that's why. So please be aware that. So let's address this problem first, and then we're going to do that one and then this one. So because many students get to this point and then they freeze, they don't know what to do with it. There's a good reason why, by the way. If you if you if you feel funny about this case, um, there's a good reason why. Don't worry. There's nothing wrong with you. It is just unexpected. 3. So let's say you have, let's keep things simple. X plus y equals 6, and then 2x plus 2y equals 12. Okay, notice that the two equations have exactly the same solutions. 3 and 3 is 6, so that is a solution to the two of them. 3, 3. How about 1 and 5? Oh, but I didn't check this one. 2 times 3 is 6. 2 times 3 is 6. 6 plus 6 is 12. So 3, 3 works for both of the solution, for both equations. How about 1, 5? Well, 1 plus 5 is 6. 1, 5 works for this equation. 1, 5 works for this equation. Let's make sure. 2 times 1 is 2. 2 times 5 is 10. I don't have 10 fingers, otherwise I would go 10. So 2 and 10 is 12. It works. So checks, checks. How about negative 1, 7? Negative 1 plus 7, 6. It works. Negative 1 times 2 is negative 2. And 7 times 2 is 14. Negative 2 plus 14 is 12. That works. So we have many solutions. This represents a straight line. And if two straight lines meet at more than one point, then they meet everywhere. Now, so we have, if we draw the line, it is going to look like this. And the other line, this line, is also going to look like that. It's on top of it. It's the same line. See, that's the weird part about it. Are they 2 or are they 1? Well, yes. And when I said yes, I meant it in a funny way. Are they 2 or are they 1? When they talk. So I didn't answer the question. The answer is yes to both. It is a weird situation, I have to admit. In fact, when we look at this more carefully, we realize if you multiply this equation by 2, we end up with this equation. So they are equivalent equations, completely equivalent equations. So in that sense, but they're not exactly the same equation because this one has a 6 in it, this one has a 12. Yeah, it's just weird. They do have the same solutions. So remember in this case how one set of solutions was this, another set of solutions was that, and they overlap. Well, in this case, we have one set here, and the other set is the same. Yeah. All right, but then how do we write the answer? And that is the main thing I want to establish. Here, let me go back to this example. There's a couple of ways to write the answer, by the way. So if we have a solution, this is one way to write the answer, 3, 3. Another way to write the answer is to say, well, x has to be 3 and y has to be 3. So we can write the answer this way, the final answer. or that way. Keep in mind, though, that some teachers are very strict. Some teachers don't 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 use this as the answer. They have to be a point. Some teachers say this is the way you have to write the answer, not this one. And then some teachers are more liberal. Not when I say liberal, I don't mean politically liberal in the sense of they don't, like me, I don't care which one it is, um, unless I, in the problem specifically, ask you to write the answer as a point, or write it as x equals and y equals a number. Unless the problem calls for it very, very clearly, I personally don't care. But please be aware that some teachers have to do it. You have to do it this way, and for some other teachers, you have to do it this way. Yeah. All right. So how do we write? Because we have to write a solution. Are there solutions? Yes, there are many solutions. So how do we write the solutions? And the thing is, there's many ways to write a solution. Even if we fix one of those two ways, there are many ways to write the solution. So the question is, how do we write the solutions? Okay. Okay. So we can solve this equation for y, and x becomes what is called a free variable. That means that x can be any number it wants to be. Yeah. So if we solve this equation for y, then we have negative x plus 6, and that means that x is free. So one way to write the answer is to write down the free variable, which in this case is x, and then the other variable is dependent on the first variable. It is negative x plus 6. So instead of putting down y, we're going to put down what it is. It is negative x plus 6. So this is typically the way we want to write the answer. And we mean x may be any number. Even though it's not written, it is understood. It is understood x may be or may take any value. So this is telling us we have many solutions. We have 3, and then you have to figure out what the y value is. If x is 3, it would be 6 minus 3, which is 3. If the first variable, the free variable is 1, then 6 minus 1 is 5. So then we have 1, 5. If the first variable is negative 1, 6 minus negative 1 is 7. So negative 1, 7 would be a solution, and so forth. So this does not tell us one solution. It tells us how to generate all the solutions. But somebody could say, wait a minute, can I solve for x? Sure. If we solve for x instead, x is equal to negative y plus 6. That is acceptable. Then y is the free variable. X is dependent on y. So that means that we have that y is free, and then x has to depend on 1, and we have to write down its dependency. Negative y, sorry, plus 6. Did I run out of eraser here? I don't know, but that's a y. Sorry for the not very clean writing here. So we have, and there are actually many more ways to write this out. Those are the two basic ones, and we want to stick to one of those two. There's actually more than that. Yeah, we can artificially, yeah, somebody could say, well, can both be dependent of a third variable? And the answer is yes. That would be more of a parametric way, but I don't want to get into that. For now, there's two ways, and let's stick with those two, and that's it. Yeah. Yeah. In this case, by the way, we say that those two equations are dependent on one another. They are dependent. They depend on each other. And this is the way we write the solution. There is another way to write a solution. Just so this is the way, the point way, you know, as a point, x, y. Can we write the solution this way in this scenario? And the answer is yes. You can say x is x, which is again weird, but remember, this is the weird case, comma, y equals negative x plus 6. So that is another way to write the answer. And it is so weird because we are writing down x equals x, which is, of course, obvious, you know, anything is equal to itself. But we want to preserve this notation, x equals something, y equals something. What this is telling us is that x is the free variable and y is dependent on the x. That's what this says. X is free. X has no restriction. It can be anything it wants to be. Y is restricted to being 6 minus whatever x is. Now you can write the answer the other way. You can say, well, y is y. That means y is free. That's how we sort of translate that into y is y. That means y can be anything it wants to be. I guess it could make sense when you say, or somebody says, I'm myself. I can do whatever I want. You know, so that's kind of what this is saying. Y is itself. It can be whatever it wants to be. But in that case, x depends on y. So we have negative y plus 6. And we usually put a comma in between. So this is another way to do this. So there's an or, this or that. If we're using point notation, if we're using, so make sure you put parentheses for the point. If we're using equation notation, then do this or that. And I wanted to address this case right away, as soon as we could, because sometimes I personally neglect this, and then students get questions like this on assessments and quizzes and tests, and then I feel there's not enough, we haven't gone over this long enough to actually come up with a right answer. So this time I'm saying, no, let's head this from the beginning, and that's it. So is this weird? Yes, because we don't end up with a solid number like 3, 3, or solid numbers. We end up with a variable and then a dependency of the other variable, and that makes things weird. We accept it as a valid problem, and there's an infinite number of solutions. How many solutions? How do we know that? Because x can be anything it wants to be. It can be 1, it can be 2, it can be 3, it can be 4, it can be 5, it can be 6, it can be 7, it can be 8, it can be 9, it can be 10, 11, 12. So how many of those do we have? Well, an infinite number of them. And that doesn't even count the fractions. You know, the x could be, 1/2 or 2/2 or 3/2 or 4/2 or 5/2. Or it can be some kind of irrational number like square root of 2 or square root of 3 or square root of 5, square root of 7. It can be any number. So is it weird? Sorry to keep repeating this, but the reason why I'm saying is because I don't want students to feel lost in this case. If we embrace the weirdness of it, then we start embracing it, we start accepting it, and we say, okay, I know how to deal with this. Yeah. Good. I hope that helps with that case. Now let's look at the second case. Well, I didn't put them in order. Again, the numbering of the cases is arbitrary. I probably should have called this number, because that was like the first case, then 2, and now I'm going to do this as 3, but it doesn't matter what we label them. So case, that's another case. So let's address this case. Okay, so we have something like x plus 6 x plus y equals 6. Sorry about that. X plus y equals 6, and then x plus y equals 12. So I'm doubling the output, the constant, without doubling the inputs. Okay, that is going to be a problem. what are the solutions here? Let's just write down a few of them, such as 1, 5, or 2, 4, or 3, 3, or -1, 7. And there are many more, even with fractions and so forth. What are the solutions to this one? Well, 111 is a solution. What about 210 is a solution? 3, 9, because 3 plus 9 equals 12. 2 plus 10 equals 12. 1 plus 11 equals 12. We can have negative numbers. -1 and 13 is another one. So we can have many. So here we have a set of solutions, and here we have a set of solutions. And guess what? They do not intersect. There is no solution that is valid for this or good for this equation and good for that equation as well. So in this case, we have to clearly state no solution. And if you want to emphasize whatsoever, whatsoever. Okay. But the main thing is the no solution part. Once you say there's no solution, it is implied that there is no solution whatsoever. Okay, so there's no solution. It's not going to happen. We cannot satisfy the two requirements that two numbers added together is equal to 6, and then the same two numbers added together is equal to 12. That is the key. The same two numbers have to add to 12. I mean, that is a contradiction. If two numbers add up to 6, how can the same two numbers add up to 12? There is a clear contradiction. It won't happen. And that's typically the case when we have parallel lines. If we were parallel different lines, let me go back to this case, because somebody could ask, or could say, are those two lines parallel? Is a line parallel to itself? Which is a good question to ask. In algebra, the answer is yes. A line is parallel to itself. And even in geometry, I have to check the books, Euclid's books, because they say two lines are parallel if they don't intersect, and then you may say, well, those intersect, so they're not parallel. But I think and I have to double check, I think when they say two lines, they mean two different lines. So they just avoided, if what I'm saying is correct, which I have to double check, then the Greeks avoided the situation when one thing is itself can be compared to itself. They just avoided that situation altogether. But I don't know, I have to double check. Anyway, so lines, pretend those are two are parallel. Sometimes the symbol we use is we put an arrow in going in the same direction, and that indicates that they are parallel. So one goes through 0, 6, the other one goes through 0, 12, and they keep the same distance from each other across the whole plane, and consequently, they're never going to intersect. They don't have a point in common. They don't have a solution in common. So the thing we have to say is no solution. And that's it. We don't put x equals anything, or y equals. So in this case, that's one of the things I wanted to drive, is that we do not use, a point. What are we going to put there? There's nothing intersection, or with them, nor do we use x equals, blank, y equals blank, because there's no solution. We simply say there is no solution. There is no solution whatsoever, or any solution. Some people use the empty set. I'm not going to use it. I'm just going to say in words, no solution, and that's it. Leave it at that. Okay. So let's go back to algebraic methods now. Algebraic methods. We're going to have substitution, elimination. And actually, there are more than those two methods. There is what is called Cramer's rule, but we're not going to see that. Those are the only two methods we're going to see. So in this video, there are more methods. Yeah, such as Cramer's rule, and then there is matrices. So there's a few different methods. People spend a lot of time in this kind of problem, in systems of equations, because it is an important topic and it has many, many applications. But we're only going to do two methods. This is the favorite method of many math people. So including myself, I have to say, yeah. So this method is preferred. We prefer this method. One reason among all many, many reasons is that this method is easy to put into a computer. It's easier to write a program for this method. This method is much more difficult to write a program for, but this one is fairly straightforward. So that's why we prefer that. Also, matrices. Again, we're not going to do matrices in this video, but matrices can be used. What is called the augmented matrix can be used, and then we eliminate, and we get very, very nice results with elimination. Elimination is preferred by a long shot. I mean, by far over substitution. Yeah. Let's go back to the example we started with. Example 1. Oh yeah. So we're gonna, even though I'm using the same equations, I'm gonna label this as example 5. So we have 2x plus 3y equals 15, and then x plus y equals 6. And we want to solve this equation, this system of equations, by the way. Before I move on, as long as we have this still in front of the camera, there is substitution, there's elimination, and there is also a combination of the two. There is a substitution, elimination, and also a combination of the two. We can start with elimination and then continue with substitution, or you can start with substitution and then use elimination. So there is also a combination of the two. We don't have to stay with one all the time over the other. But again, because of matrices and computer sciences, as far as being able to write a program to solve equations, elimination is always preferred without any substitution. There's another reason. Elimination also gets to the weird cases very easily. Yeah, substitution doesn't do such a good job solving the weird cases. Yeah. So let's focus on substitution right now. Anyway, so solve for one of the equations, one of the variables, or for one of the variables in one of the equations. It doesn't matter which one. Now, we typically pick an easy one, such as the second equation. So for instance, here, we can solve for x, this equation. And so x equals negative y plus 6. All we do is subtract y from both sides of the equation. And then we substitute this back into the second equation, or the other equation. And that's going to give us 2 times not x, but the quantity negative y plus 6 plus 3y equals 15. So what we gain with that is that this equation has no x in it any longer. So we have 2 times negative y is negative 2y. And then we distribute the 2 with the 6 plus 12. Keep the 3y equals 15. Okay, 3y minus 2y simplify down to a single y. And I'm going to move the 12 over. So 15 minus 12, 3. Okay, so now that we have y equals 3, we can put this back into this equation. And that's going to give us the x value. So x equals opposite of y. Y is 3, so its opposite is negative 3 plus 6. So x has to be 6 minus 3, 3. And voila, we have x equals 3, y equals 3. As you can tell, this is a little bit messy, you know, because we get to this point starting with that equation, then we're going to go back to here. We end up with this equation, which we solve, and then we substitute back into this equation, which was kind of mid-range, and then we come up with this, for which we solve, and that gives us the x and the y value. Yeah. Substitution can be quite messy if there is nothing to solve for very easily. So example 6. Okay, let's say you have, okay, so here it goes. This is going to be not an easy problem. 5x plus 4y equals 6. 2x plus 3y equals 2, 3, 4, 5, 6. So let's put 7. Okay, I just want to use different numbers all around. So this is a new problem. We haven't done this problem. Substitution. Okay, let's do the substitution. Which variable are we going to solve for? Which variable? Which one? Well, there's no easy one. I mean, in the previous example, solving for x was easy because all I had to do is bring the y over. Here, we got to bring this, if I want to solve for x here or here, we got to bring this quantity over, and then we got to divide by 2. And we're going to end up with fractions. Okay, and the same thing here. So it doesn't, how difficult they are is about the same, solving for x or for y on this equation, on that equation. The degree of difficulty is going to be the same. We got to bring the other quantity to the other side. We're going to divide by the coefficient. Okay, so let's do it. So this equation, I'm going to do it in 2 steps. 2x equals negative 3y plus 7. And then we're going to divide by 2. So x is, negative 3 over 2y plus 7 over 2. Okay, then we put this into the other equation. And it doesn't matter which one you start with. You got to put it back onto the other equation. All right. So then what happens? We have 5 times the quantity, negative 3 over 2y plus 7 over 2. So 5x, don't write the x, write what it is equal to. Plus 4y equals 6. Now we have an equation with only one variable, just the y. Sorting this out is going to be, a task. So multiply by 5, we got negative 15 over 2, 5 times 3, y, plus 35 over 2, okay, plus, now I'm going to think ahead. I'm going to plan ahead. I'm going to combine the two y's. This y with this y. So this one is already in halves. Anticipating we're going to combine them, I'm going to change this 4 into halves. 8 halves y equals, and all of those are fractions with halves. So anticipating we're going to combine fractions together, I'm going to make this 6. I'm going to turn the 6 into 12 halves. If we don't do it ahead of time, then we have to eventually do it at some point. You know, we're going to add fractions or numbers with fractions. So must just as well have a common denominator off the bat. All right, so those two are -7 halves. Actually, at this point of the game, we could multiply the whole equation by 2. Why don't we do that to get rid of the fraction, at least initially? So we have -15y plus 35 plus 8y equals 12. Multiplying everything by 2 times 2 times 2 times 2 times 2. And now we can simplify more easily without the halves. -7y, combining those two. We're going to bring the 35 over to the other side of the equation. So we're going to end up with negative. If we subtract 12 minus 35, we're going to end up with 23, if I'm not mistaken. Yep. And then we divide by 7, rather -7, and we end up with y equals, the negatives are going to simplify, positive 23 over 7. Okay. Then we put this y into this x so that then we can get an x value. So we got y. We can box it. There is y. And then x is equal to -3 halves of y, but y is 23 over 7. Plus 7 halves. Well, that's going to give us -3 times 23 is 69. -69 over 2 times 7 is 14. Nothing simplifies. Plus, okay, 7 halves. Anticipating we're going to add this fraction with this fraction, I'm going to change that denominator into 14. So we multiply the numerator and denominator by 7 to get the 14. So 7 times 7 is 49. 2 times 7 is 14. And now we can combine those nicely. That's -20 over 14. So I'm going to continue the equal sign here. Yep, -20 over 14, which simplifies down to -10 over 7. Okay. So now we got the x value, which is -10 over 7. And I'm going to box it. Okay, so we got x value, y value. Can we do this problem with substitution? Absolutely yes. We just have to be extra careful with the fractions, with the solving. It is a little messy, and we got to keep track of what's going on, and we got to be very careful. Okay, so that is the method of substitution. There's a lot of stuff going on, a lot of keeping track of what's going on, because you solve and then you plug in and then you solve again and then you plug in again, and there's a lot of solving and plugging in and solving and plugging in kind of thing. Does it work? It works really well, but not as good as elimination. Elimination works even better, much better. This is way neater if we apply elimination. Let's redo this problem using the method of elimination. Okay. 5x plus 4y. I'm just copying the problem, making sure I'm copying it correctly. 2x plus 3y equals 7. Okay. So let me show you. Multiply. So we want to eliminate the x. And by doing that, if we have matching coefficients, if those two coefficients were the same, we could subtract one equation from the other, and the x's will go away. They're not matching, but that is an easy thing to fix. We can match the coefficients. Multiply this, the whole equation, by 2. And that's going to give us 10x plus 8y, don't forget to multiply everything in the equation, equals 12. Multiply the second equation by 5. Now, how did I know that? Here's the question. Are the coefficients the same? Is 5 equal to 2? No, obviously not. This coefficient has a 2, and that coefficient has a 5. So what we do is give to the equations the coefficient that is missing, that the other equation has. So this one has a 2, give a 2 to this equation. So that equation will have a 2 now. Give a 5 to this equation because it does not have a 5 while this one does. And that way this equation has a 5 now. So that's why we multiply a 5, to give this a 5 to this coefficient. So we end up with 10x plus 15y equals 35. Now we have that coefficient has a 2 and a 5, that coefficient has a 2 and a 5. Of course, they are the same coefficient, so now we can subtract. The equations, 10x minus 10x, no x. 8y minus 15y, negative 7y. 12 minus 35, negative 23. A simple division, y equals 23 over 7. But the drama has been gone down compared to the substitution method. We did get the same answer, y equals 7/3, y equals 7/3. In my opinion, there is more drama here. Oh my goodness, what are we going to do? Which one are we solving for? Where are we going to plug it in? What if I solve incorrectly? I mean, you can still do a lot of things incorrectly here. No, don't take me wrong. But I think this is way simpler. There's another reason why elimination, which I'm going to tell you in a moment, is preferred. Say you have, we eliminated the x. Now let's eliminate the y. So I'm going to start all over with the same system of equations. 5x plus 4y, 2x plus 3y, 6 and 7 respectively. Let's multiply. I'm going to go down a little bit because I don't want to bump into this. Okay, so we want to eliminate the y's. This y has a 4, this one doesn't. This one has a 3, the other one doesn't. So we're going to give to each other what the other one has and what they don't have. So this one has a 3, and that y doesn't have a 3. Let's give it to it, multiply by 3. Now the catch is that we have to multiply the entire equation by 3. 15x plus 12y equals 18. Multiply this by what the other equation has, which this one doesn't have. So we're going to multiply by 4. 8x plus 12y equals 28. And now we're going to subtract one equation from the other. 15x minus 8x, 7x. 12y minus 12y, no y. 18 minus 28, negative 10. Let me just double check before I write down the final solution. Oh yeah, we're good. Divide by 7, and we get that x equals negative 10 over 7. Here's the x, here's the y, and we are finished. I think this is less drama than substitution, but there is something else that I think is relevant. Substitution has a flaw, and this is it. It is sequential. Substitution is sequential. What I mean by that is, okay, we solve for y, and then we used the value of y to figure out x. Okay, so we put this y that we found, put it back into this cycle to get the x value. That is a flaw in the sense that the solutions are not independent of one another as far as solving. Had this y been wrong, had I changed a number, had I made a mistake somewhere along finding the y value, that mistake will carry over to figure out x. So the solution is sequential, which adds to the probability of getting both of the answers wrong. Now, I'm not saying that will happen, but it adds to the possibility. Yeah, that's why important people, such as the CEO of a company, and then the controller of the company, the accountant, they both, their signatures can sign checks in a company. So they're very important people in a big company because of their signatures. They have the power of signature. They can sign a contract, for instance. You don't want to keep them in the same plane or in the same car too often, because if there's an accident, then the people who are responsible for something important, something could happen to them, and then we have no person. So when something is very, very important, such as the signature of a person, you want to keep them in separate vehicles, in separate planes, in separate places, so that the probability, and this is all probability, of something going wrong is less because you keep them separate. That's kind of what is going on here. This solution, using pure substitution, this x solution relies 100% on this solution. If this is wrong, that's going to go wrong automatically. They're both going to be wrong. In the elimination method, we did not rely on y to figure out x at all whatsoever. We started the problem from scratch. You see, I copied the problems again and started a process independently of this. Now, that doesn't mean that they're both going to be correct. What that means is that if I got this wrong by making a mistake, then it could be that this is still good while this is wrong. Yeah. Now you may be thinking, well, it could be that you're right here and then wrong there, because the mistake could happen after finding this correct answer. Yes, true. Yeah. So we got to work out the probabilities. That is a good probability problem. Which one, assuming that the mistakes that can happen are equally likely in either case, which method is better? And in my opinion, I have to do the probabilities to actually come up with the solid numbers, but I think it won't take too long to figure out that this is better, elimination is better, as far as making a mistake and avoiding carrying one mistake into the next step. Yeah. Let's do another example, 8. Let's say we have 3x minus 2y equals 5. So I'm just making up a problem. So 2, 3, I didn't use the 4 yet. Negative 4x plus 6y equals 7. There we go. Oh, by the way, it is very, very advisable. I recommend to, once you get a solution, especially if you're taking a test or a quiz where this problem would be a lot of points, to take this problem this solution and put them back into the original problem to make sure that we actually solve the two equations. Those two numbers do solve the two equations at the same time. Okay. I'm going to apply the same method. Now, I'm not going to worry about the plus or the minus. I'm going to take care of that in the second step. So we multiply by 4. This one has a 4. This one does not have a 4. We're going to give it a 4. This one has a 4, but it doesn't have a 3. We're going to give it a 3. I'm not going to worry about whether those are positive or negative. So 4 times 3 is 12x minus 8y equals 23. So negative 12x plus 18y equals 18. And then you're going to say, okay, so now we're going to add, rather, we're going to subtract this minus this, because that's what we did in the previous example. We subtracted, and that's the way we got rid of the 10x and the 10x. Well, if we subtract, we're not going to get rid of the 12x, because this minus negative 12 is going to give us positive 24. So instead, we're going to add. And then you may be thinking, oh, how come we subtracted and we added here? Because we're going to add or subtract. So here's the rule. Add or subtract, comma, whichever eliminates the variables or the variable. So I'm not going to worry about that. I'm going to worry about that here. So it's interesting because this process calls for your judgment. You have to decide whether to add or subtract on your own. You got to think on your own. And that's a good thing. You got to think on your own. You got to make a judgment. Am I going to add or subtract? I'm not going to tell you. You got to observe the situation and realize, well, one is positive and the other one is negative. So if we add, they're going to add up to 0, which is what we want. We want to eliminate. When we observe the situation, we realize they both are positive. So if I add, that's not going to eliminate the variable. We need to subtract. So we have to make a judgment call. It is not just like the quadratic equation where you just plug in the numbers and there's the answer. No. Now we got to start making some calls. Should I add or should I subtract? And some people will say, well, they have a rule. You know, if they're both positive, then, you know, you can multiply by a negative, which is valid. By the way, that's the other thing. If at some point in some other course, whether in high school or before or after, you know, they tell you one has to be positive, the other one has to be negative, go right ahead. They're doing the thinking for you when they do that, which is fine. That's not necessarily wrong. I like to leave things a little open so I can make judgments along the way if needed. So in this case, I'm going to add, not subtract, because that won't achieve what we want, which is to eliminate the variable. So adding those two means 0 because 12 is positive and this other one is negative. Adding those two is going to give us 10. Adding those two is going to give us 38. So y will be 19 over 5. I know that threw you off, I bet, because I didn't tell you that after doing 38 over 10, I simplified the 2's. Yeah. Initially, we do get 38 over 10. I just did a fast one on you because after that, then I simplified in my head, well, the 38 is 2 times 19 and the 10 is 2 times 5, so we can eliminate the 5's, rather the 2's. Anyway, so 3x minus 2y equals 5. negative 4x plus 6y equals 7. So let's use the elimination method. But now this time I want to eliminate the y's. Okay, now there is two ways to do this right now. You can say, well, multiply by 6, multiply by 2, and then move on. And that will work, however. However, we can be a little more efficient. You know, this one has a 2, and this one already has a 2, correct? The 2 is embedded into the 6. 2 times 3 is 6. So there's a 2 already here. What I could multiply by this guy is 3, and that will create a 6 here, which will match the 6. Remember, our goal is to match the coefficients. If we can achieve the matching by something simpler than throwing a 6 in there and throwing a 2 in here, we should. So we multiply this by 3, 9x minus 6y equals 15. Since this already has the 6, again, we're making a judgment call. We're saying, hey, we already got what we wanted. So there's no, if you want to say something, you can multiply by 1 or just leave it alone. Negative 4x plus 6y equals 7. Don't do anything to it, leave it alone. Now we want to simplify that. So I start thinking, see, I don't know about you, but I like when we pause for a moment and then we think, hey, what should I do next? And for some of us, it can take, 2 minutes. What should I do next? As opposed to having a process that everything is automatic and you just crunch the numbers. I prefer the thinking, the deeper thinking of what's going on. So here we add the 2. That's what I was thinking that we need to add, because this one is already negative, this one is positive. When we add a positive and a negative of the same magnitude, we end up with nothing, with 0. 9x plus negative 4x is 5x equals 22. So of course, x is 22 divided by 5. There is our y, there is an x, and voila. Nine. Let's say we have x plus y equals 6. 2x plus 2y equals 12. And we want to use the elimination method. Okay. We want to eliminate the x. This one has a 2, this one doesn't. So we can multiply this by 2, and we have 2x plus 2y equals 12. And this one is already 2x plus 2y, so multiply by 1, as in the previous example. 2y equals 12. Now, we may be thinking, okay, I want to eliminate the x. Both are positive, so we want to subtract. 2x minus 2x, no x. 2y minus 2y, no y. 12 minus 12, 0. So we end up with an identity. This is called an identity. When an equation is always true, that is called an identity. Okay, if you have an identity, okay, that means that we have infinitely many solutions. We have all, that means that the two equations are dependent on one another. Yeah, they're dependent on one another. And that means that we have an infinite number of solutions. We have hundreds and hundreds of solutions. How do we write the solutions? This goes back to our example. Looking back, example 3. So this is exactly example 3. And if we solve for y, y equals 6 minus x, that means that x is a free variable. So one way to to write the answer is x comma negative x. Oh, I wrote it wrongly. And I have to get a new eraser, but so I'm just gonna cross that off, negative x comma, and then, oh, here we go again, boy. X, that would be our free variable, and then y would depend on x. Y would be negative x plus 6 when we move this x to the other side. Negative x plus 6. If you write down 6 minus x, that's fine. But that would be one way to write all the solutions. Or we can set y to be free, so we move it to the other side of the equation, and then x will depend on y. So, or negative y plus 6 comma x. So that is another way to write the solution. I meant y here. Whoops. Yeah. There we go. Whoa. Now, this case is very tricky. Just embrace it. It's weird. It's tricky. It's not common. It is what it is. Just embrace it. That's my take on it. Okay, 10. X plus y equals 6. X plus y equals 12. Okay, they already have the same x, the same coefficients, 1 and 1. So if I'm going to use the elimination method, there is no need to multiply by 1 and multiply by 1 if we're going to end up with the same two equations anyway. Here, that equation was the same, but that equation wasn't. And I wanted to line them up one above the other so we can do the subtraction. So that's why I copy this over, because this one is had to be multiplied by something to match them. In this case, they are the same already. So again, we got to make a call. We got to analyze the situation as we go. We want students, citizens of this world, to be able to think things through as we go along. We don't want to just copy one thing and I mean, don't take me wrong. Sometimes it is handy. I'm not being an absolutist, don't do this all the time or don't do that all the time. No, sometimes having a process, number of steps to follow is good. So I'm not throwing that, don't throw the water with the baby. No, it goes the other way because you don't want to throw the baby. Don't throw the baby with the water. But I'm not saying having a list of steps to follow, such as with the quadratic formula, is a bad thing. Sometimes it is handy because you want to move on to the next part of the problem. But it is also handy to pause and think and, okay, what do I multiply by? Well, look, they're the same. So there's nothing to multiply by. Might just as well subtract at once. Subtract x minus x is 0, no x. Y minus y is no y, so there's a big 0. 6 minus 12 is negative 6. 0 equals negative 6 is a contradiction. Contradiction. That's a contradiction. If at any point in the solving of a problem, a system of equations, you end up with a contradiction, review your steps to make sure you did not make a mistake. If after reviewing a couple times and noticing that there's no mistake, if you still end up with a contradiction, that means there is no solution. That implies no solution. No solution at all whatsoever. There is no solution to this problem. Yep. Yep. So sometimes there's a solution. Sometimes we have infinitely many solutions. Sometimes there's no solution at all. Those are the three cases. I was going to do 3x3 systems of equations, but I think I'm going to leave that for a new video. So yeah, for the next video, we're going to do 3x3 systems of equations. All right, we'll stop this video here.